Everyone, I'm Nirubam and I welcome all of you to Sort of Sus classes. I hope you are having a nice time. So today I will be talking on the expenditure function as part of the duality theorem. Okay. So expenditure function. I will be talking about the properties of this expenditure function. So if let's say if you're assuming that the indifference curves the preferences are the indifference curves are strictly convex to the origin, and the optimal amount, that means as per the cost minimization problem subject to given level of utility, the optimal amount of xi that is required to minimize the expenditure subject to a given level of utility should also vary smoothly and continuously with a change in the price of any of these goods as well as also with the given level of utility. So the demand curve, in this case the demand curve which you are deriving for each of these commodity for each of these goods is nothing but the Hicksian demand curve, and if these two conditions are satisfied, that means the indifference curves are strictly convex as well as optimal consumption bundle, and hence the optimal amount of consumption of each of the goods in the bundle varies continuously smoothly, then the corresponding Hicksian demand function should also be continuously differentiable, and then the slope of this the Hicksian demand function will give nothing but the substitution effect of the price change. So this substitution effect of the price change will be given nothing by this expression, that is del hi of del pj, where hi p of u gives you the optimal amount of consumption of the iron good in the commodity bundle so as to minimize your expenditure subject to this given level of utility u and the given price vector t. Now then we derive, following this we derive this minimum expenditure function which is given by pi of xi star is of npu. So this is the minimum expenditure function. Now this minimum expenditure function has got certain properties. So what is the certain properties? So the certain properties which we have is that first of all this is concave in prices. So the expenditure function is concave in prices. That means if there are two price vectors, that is P star and P prime and P double prime, then we consider a number k such that it lies between 0 and 1, both the limits included, and then we construct another price vector P bar such that it is equal to k of P prime plus 1 minus k of P double prime, okay, k of P prime and k of double prime, then and P respectively, so P prime and Q prime. So when we have got P prime as our price vector, then the optimal consumption bundle at which the expenditure will be minimized is given by x prime. Similarly, when P double prime is the price vector, then the consumption bundle at which the expenditure will be minimized is given by x double prime. And similarly for P, the cost minimizing consumption bundle is given by x bar. Then if these are the conditions which we have, then if the expenditure function is concave, then we will have this following expression, that is P bar x bar is greater than or equal to k of P prime x prime plus 1 minus k of k double prime x double prime. So this is nothing, this can be written again as here. So the utility here remains unchanged under only three different price vectors. K of n P prime u plus 1 minus k okay. Now the question is that how we can actually prove this. So we can actually put this in the following way. Let's say, as I have already mentioned, that corresponding to the price vectors P prime and P double prime, X prime and X double prime are the cost minimizing consumption bundles subject to the given level of utility U. That means for P prime we have got X double prime, which is cost minimizing, and for P double prime X prime, and for P double prime we have got X double prime. Now for P bar, the cost minimizing vector is given by X bar. Now this is only a unique relationship. So for X prime it is only, for P prime it is only X prime that will be cost minimizing. For P double prime it will only be X double prime that will be cost minimizing. And for P bar, the X bar is something which is cost minimizing. So these three different consumption bundles will be cost minimizing for corresponding to different price vectors. Now if this is what follows, then we can write easily that Px bar is at least as expensive, if not greater than P prime X prime, and similarly for P double X bar is at least as expensive, if not more expensive than. Now multiplying this cost inequality by k and the second inequality by 1 minus k, and adding both sides, we get the following expressions. That is k P prime X bar plus k double prime X bar is greater than equal to k P prime X bar plus k 1 minus k. So this is 1 minus k P double prime X double prime. Now we can write this taking X bar, so we can write k P prime plus 1 minus k Okay. So we know already what is this k P prime plus 1 minus k P double prime. So this is nothing but equal to P bar. So P bar X bar is that will be equal to k of P prime X prime plus 1 minus k of P prime X bar prime, which can be written something as n by P bar U k of n P prime mu plus k of m P double prime u. Okay. So this proves, and hence this proves our assumption, and hence this proves our property, that is the expenditure function is concave in prices. Now if you would like to show this diagrammatically, so if you are showing this thing diagrammatically, so how can it be shown diagrammatically? Let us see. Okay. Now this is the ISO expenditure line with the price vector P prime. Okay. So this is the ISO expenditure line corresponding to the price vector P prime, and also it contains a consumption bundle X prime, that is a cost minimizing consumption bundle subject to a given level of utility U. Fine. So here this is my consumption bundle X prime. Now subject to the price vector P double prime, my ISO expenditure line will be given by this one. So this is corresponding to the price vector P double prime, and it also contains optimizing bundle X double prime, and hence let us assume that the X double prime is here. Okay. Now, if you are joining these lines, let's say we are joining these 2 points. So we are now joining these 2 points. If you see, we are joining these 2 points, and let's say the consumption bundle X bar now lies somewhere. The consumption bundle X bar is now lying somewhere. Let me draw this possible. So we can now draw also the indifference curve. Okay. So this is the indifference curve, and we can see that, let us assume that the new consumption bundle is again on this, that is X bar is again on the same indifference curve. So as we keep on shifting these ISO expenditure lines given the same price vector, that is P prime and P double prime, it is obvious that as we keep on shifting it, so both these ISO expenditure lines will have to keep on shifting outward, and hence further away from the origin, and as they move further away from the origin, then that will imply higher ISO expenditure lines and higher level of expenditure, such that both these lines are passing through this point X prime. So it is very understandable geometrically speaking that as we keep on shifting these 2 ISO expenditure lines outward to pass through this point X prime, that is on the same indifference curve as X prime and X double prime, so we will have to incur higher level of expenditure, and hence this also gives geometricalization to the expression, that is P prime X double prime is greater than or equal to K of P prime X prime. P bar X bar is greater than or equal to P prime X prime plus 1 minus K of K double prime X double prime, and hence it shows that why the expenditure function is concave in prices. Now there is an issue which we can find. So here we are getting this geometrical assertion because of the shape or the structure of the indifference curves only. So here this inequality is being satisfied as a result of the particular structure of the indifference curve. But if we look, when we derive this expression for the concavity of the concave, when we derive this property that this expenditure function concave prices, we did not need any assumption about the structure of the preferences of the indifference curves. So hence it did not depend on the convexity of the indifference curve. So here you can see that the indifference curve is convex, but when we derive this property, we did not need this property of the convexity of the indifference curves. But we all know that for the friction demand function to be continuously differentiable, that is number 1, as well as and hence for the expenditure function also, and for the uniqueness, that is for the optimal solution which should be unique, as well as for the differentiability of the friction demand function expenditure function, we needed the convexity of the indifference curve. That is the thing we need to keep in mind. Now we also know that the strict convexity of the preferences also implies strict concavity of the expenditure function for an interior solution to the problem, rather than having a corner solution. So if you are having an interior solution to the problem where positive amounts of all the goods are being bought, as we try to assume when we are trying to solve the cost minimization problem in subject to given level of utility, then by that assumption we itself imply the strict concavity of the expenditure function. Fine. Now, the next property which we will be deriving with respect to this expenditure function is this, that the slope of this expenditure function at any point gives the optimal amount of the good that is being consumed of an optimal consumption of an ith good that is being consumed as the price of that good changes by an infinitesimal amount. So how this is being obtained? So this property is something which is known as the Shephard's lemma. So what does Shephard's lemma say? So the Shephard's lemma says that the slope of the expenditure function at any point is equal to the compensated demand for the good I at that point. So that's how we are getting this Shephard's lemma. So Shephard's lemma can be written mathematically as follows, that is del m of del pi is nothing but xi star. Now how we can write? So we know m is nothing but a function of p and q. So when we are differentiating this function with respect to the ith price of price of the ith commodity, then we get the expression as follows, that is xi star plus that is pk. So this is pk and xi star, and this is nothing but pk del xk divided by del pi. Okay, del xk star divided by pi. So we have to derive this expression, we need this part equal to 0. So how we are getting this part equal to 0? So when we are doing the optimization for the cost minimization problem, then the first order condition, one of the first order conditions given something as is, that is del of del xi equal to pi minus mu of ui equal to 0, which means pi is equal to mu of ui. So here we can write pk is actually equal to mu of uk. And again, if you remember the other first order condition, that is del L of del mu equal to u of x1 to xn equal to 0, which is nothing but u of x1 to xn equal to u. So when we are writing this, then we know that the value of this utility function is a constant. So if you are trying to differentiate this utility function, then and we are having a constant value of the utility function, so if you are doing del u of del xi, so it will be essentially equal to 0. So uk here is essentially equal to 0. So as this is essentially equal to 0, that means this expression turns equal to 0, and hence this expression is equal to 0, and hence we get the summation of all these expressions equal to 0. So we are left only with this part of the differentiation, that is xi star. Now if we are putting this thing graphically, let's say, where we are putting price of good on the horizontal axis and expenditure on the vertical axis, and this, then we get this our expenditure function, that is as the price is increasing, then this is our expenditure function, okay, that is in P of Q. So here this expenditure function is corresponding to a given level of utility. So for different levels of utilities, we will have different expenditure lines. Okay. Now, if we are drawing a tangent, let's say we are drawing a tangent to this point. Okay. So this value of this tangent, that is del L and del pi, is nothing, as we have shown, it is equal to xi star, which is nothing but the value of the Hicksian compensated demand function. So the slope of the expenditure line at any point gives the value of the compensated demand of the ith good at that point. But we know that the change, this result is applicable only, if you see graphically, this result is applicable only when the change is very infinitesimal or the price change tends to 0. But we know for all practical reasons that this price change is a finite value and it is not an infinitesimal value. So hence here this slope will actually tend to overestimate the change in expenditure that is required when the price of one of the commodity changes, so as to keep the consumer at the same level of utility, because we have got this utility constraint. Because what is happening is this: following the change in the price of that good, there is not only the own substitution effect, but there is also cross substitution effect. So as we are changing the price of that good, so we tend to reduce, let's say if we are increasing the price of the good, we tend to reduce the consumption of that good, while we tend to increase the consumption of the other goods, so as to keep us at the same level of utility and hence minimize the expenditure as much as possible. So this expression is nothing approximate, so this is approximately valid only in the price change is infinitesimal and not a finite positive value which is greater than 0, far away from the 0 value. Okay. Now the other property of the expenditure function is this, that as the price, so the other property of the expenditure function is this, that is del m of del pi should be greater than or equal to 0. So if you are consuming positive, the prices are positive, and if you are consuming positive amounts of each good, so as the price is increasing, so we have to understand that as the price of one of the good is increasing, then we need to have at least the same level of expenditure, if not high level of expenditure, to maintain this same level of utility. Okay. So this is following, as I said, that it is following from the fact that the optimal level of consumption of the ith good is always greater than 0. So this is always non-decreasing in the price vector. It is non-decreasing in the price vector as is evident from this inequality sign, and it is strictly increasing in at least one of the prices. Now further, another property is this: the expenditure function is homogeneous of degree 1 in prices. So let us assume there is a given price vector and a level of utility is 0, and the expenditure function that minimizes this expenditure is given by m of p 0, m of p u 0. Now let us assume that the price of all the goods changes by a given factor k, where k is, let's say, greater than 1. Okay. So now the price changes from the price vector now changes from k to kp. So we have to understand that the relative prices of all the goods remains unchanged, and hence the consumer is again at a new, so hence the consumer is facing a situation where the highest expenditure lines will have the same slope compared to the initial situation, and hence this same consumption bundle, that means as the so-called ISO expenditure line remains unchanged, and that means we will have the same cost minimizing consumption bundle that was minimizing the cost in the earlier situation as the solution to the problem when the price has changed from k to kp. That means now the expenditure will change from px0 to kpx0 because the consumption bundle remains unchanged as a result of relative prices remaining unchanged. So when this happens, so that means expenditure function, so that means the expenditure function now changes from mkp u0 to mk of p to u0, which is nothing but k of p x0, which is again nothing but k of m of p u0. Okay, and hence this proves our property that it is homogeneous of degree 1 in prices. Now, as we know that this expenditure function can be written, if you see, that is expenditure function a of p of user. So we can see that this is a function of price as well as utility, which is nothing but this expression, that is summation over pi of xi star, where xi star is nothing but the optimal consumption of good I that minimizes the expenditure with a given level of utility, and this optimizing consumption bundle is nothing but action compensated demand, which is again a function of P and U. So we can see that this expenditure function is a function of P and U, and it is monotonically increasing. That means if we decide to vary either of these parameters, that is the price vector or the utility, the expenditure function will be non-decreasing in utility. So it will be, actually it will be not non-decreasing, but it will be strictly increasing in utility. Why? Because let us assume that if we have kept the price vector unchanged, that means the relative prices remains unchanged. So the slope of the ISO expenditure line remains unchanged. Now the given ISO expenditure line, say for M2, is tangent to a given indifference curve I0, which is representing a given level of utility U0. So that means M2 is the lowest ISO lowest is representing the lowest expenditure that is required to reach this level of utility. Now as we shift these indifference curves outwards from I0 to I1 and further to I3, then they are representing higher level of utility. Now with the same price vector and hence relative prices, the ISO expenditure line has to now shift outward such that they can be tangent to the higher indifference curves, and these points of tangents and the ISO expenditure lines which will be tangent to this higher indifference curve will represent the lowest expenditure that is required to achieve those level of utility. Now we can see that the price vector remains unchanged, and hence the relative prices remain unchanged, and hence the ISO expenditure lines will be nothing, the higher expenditure lines will be nothing but the outward shifting of the initial expenditure, ISO expenditure lines that was tangent to this indifference curve I0. So higher ISO expenditure lines represent higher expenditure, and hence as we are increasing the utility, then our expenditure also tends to increase, and hence it is strictly increasing in U. Okay. Now we can give another explanation. So we have seen. If we look at this Lagrangian for the cost minimization problem, where we are trying to minimize the cost subject to this constraint, that is utility constraint. Then we have got the following first order condition, that is del of del xi equal to pi minus mu of qi equal to 0, and del of del mu equal to del of del mu equal to u equal to mu minus u of x equal to 0. So here this Lagrange multiplier mu represents nothing but the change of minimized expenditure. So this Lagrange multiplier mu represents nothing but the change in minimized expenditure that is required following an infinitesimal change in the level of the utility. So this mu is nothing but representing, this mu is representing nothing but that value which is required to change the expenditure following a given change in utility, and hence it is also representing, which is something known as the marginal utility of. So it is also representing something of the inverse of the marginal utility of income, and the inverse of the marginal utility of income is nothing but the Lagrangian multiple lambda in the utility maximization problem. So 1 by lambda is nothing but equal to mu, and we know lambda is nothing but the marginal utility of income. So if you are increasing income, if you're increasing your expenditure, hence the income by a certain amount, what is the corresponding change in utility? And here mu is representing the change in income, change in the expenditure, the minimized expenditure that is required following a given change in the level of utility. So this mu is representing the marginal utility in the inverse of the marginal utility of income. So this derivation, that is del m of del u, del m of del u which we were discussing here, is nothing but the inverse of the marginal utility of income, which is again equal to the Lagrangian multiplier mu. So given the explanations which we have followed, that given a particular structure, so here if you are assuming that the references are convex and we are operating in a zone of non-cessation, so if you are increasing the increasing our expenditure going by the definition of the lambda, then there is also corresponding increase in the utility. That means when we are inversing this multiplier, that is lambda, we change to 1 by lambda, and we are getting the Lagrangian multiplier mu, which again represents the expenditure, change in expenditure that is needed for a given change in utility. Now if this lambda is positive, that means 1 by lambda is also positive, and hence we get a positive mu which is greater than 0, and hence we get the differential, that is del m by del u greater than 0. Okay. So that's all we have to discuss about the properties of the expenditure function, and I hope you have been able to understand and enjoy this lecture. So thank you once again from my side.